So here's the next no brain too small circular motion question. This one's looking at roller coasters. Everyone loves a good roller coaster. So it's a bit windy today, so you might hear a bit of background noise. Anyway, let's get into the question. Alice, luckily, she's taking a ride in a theme park, and the cart's travelling towards a circular loop. The first couple of questions are to do with, well, banked corners, and then the first bit's not really to do with the loop, but then the D is one of my favourite questions. Alright, so here we have to draw the forces, label the vectors to show the two forces that are acting on the car. So the first force that's acting on the car from the cart's centre of mass is the weight force, Fw, and the second force that's acting on the cart, acting at right angles to the surface, is the support force or the reaction force. And you kind of want the vertical components of these forces to be roughly the same. Fs. Okay, so then we're ignoring friction, so these are the two forces. Then on to question B. So B, we're given the mass of the cart, which is 9.6 times 10 to the 2 kgs, and the angle of the bank, which is 20 degrees. Now I've exaggerated this in my diagram just to make it a bit easier to complete my diagram. Okay, and we're going to calculate the size of the centripetal force. So the centripetal force, it's a total force or a resultant force, and it's due to the sum, the total of the weight force acting downwards like this, and the support force, which is acting at right angles to the surface like so, giving us a centripetal force, a net force, which is from the first tail to the last head, and this is the centripetal force here. And here is the angle of 20 degrees, and we can calculate the weight force by doing mg. Okay, I'll come back to this part in a moment. I'm just going to use the trig equation for this triangle. So for that, we're going to use tan theta, and that's equal to the centripetal force, Fc, divided by the weight force, which is mg. Then I'm going to rearrange this and make Fc the subject. So that's mg tan theta. Substituting in all my numbers. And we get a centripetal force of 3,428 newtons to 4 significant figures, just for the fun of it. Cool, so this seems like a reasonable force, thinking about how big the weight force here must be. Okay, on to the next question. So for the next question, we need to compare the force that the track exerts on the car when it's in position A, which is at the top of the ramp here, and the force when it's in position B, which is at the bottom of the ramp. Now I assume they've chosen these two positions because in both positions the car is horizontal, but there is a difference in the forces on the car. So at the top here, the car is not accelerating upwards and it's not accelerating downwards, which means the vertical forces on the car must be balanced. So again, the two forces are the weight force and the support force, and since these forces must be balanced because the cart's not accelerating vertically, I'm going to draw them the same length. Now technically the support force is split between the two wheels, but it's just easier to draw one. Cool, so these two are the same size because there's no vertical acceleration. Now over here in position B at the bottom of the loop, this time the car is in circular motion. Even though it's just come into the circle, it's started to be in circular motion, which requires a force towards the centre of the circle, the centripetal force. Again, that force is just the resultant force of these two forces. So if we need a force towards the centre of the circle, that means the force upwards needs to be bigger than the force downwards. The mass of the cart hasn't changed, so the weight force is the same as in position A. So the force that must have increased is the support force. Okay, so I'm going to draw that times much bigger, just to make it obvious that this force is bigger now than the weight force in position B. Okay, now for one of my favourite questions, we need to figure out how high h needs to be. What's this height here of the cart at the start if it's going to go around this loop at the minimum possible speed? And we're assuming that there is no friction. So this is an energy problem, and if there is no friction, that means the energy in the system is conserved. So for this energy problem, we need to consider two places. We need to consider the top of the ramp, and we need to consider the top of the loop. Okay, so here at the top of the ramp, this is the total energy that the system has at the start. So I'm going to call it E total. And the E total is going to be equal to the total gravitational potential energy at A. Okay, should I put A there? Yeah, cool. So this is the total gravitational potential energy at position A, which is the top of the ramp. And then the other place we need to consider the energy is here at the top of the loop. Okay, we'll call this position top, and at the top of the loop we've got two types of energy. So the car has risen up from here, which is where we're measuring the gravitational potential energy in position A from. So again, there is going to be gravitational potential energy, GP top, but the cart's also going to be moving, which means it must have kinetic energy, EK top. So this equation here is sort of the guts of what I need to work this out. So the gravitational potential energy at the top here is going to be equal to the gravitational potential energy here plus the kinetic energy here. So let's take this back up to the top and work from there. So let's consider this point here. At the top of the loop, the cart, the centripetal force is due to the weight force at the slowest possible speed. These two are equal. So we're going to do that same thing, which we've done a lot in these problems, is equate these two equations together. The mass of the cart cancels out, and then we're going to rearrange it to make. So the reason I'm leaving it like this is because leaving it as v squared is going to be helpful, because that's going to go into the EK equation down here. So let's start using this. I haven't given myself much space. It's a bit awkward. Anyway, let's go here. So this is gravitational potential energy. So that's mg delta h, because we're talking about the gravitational potential energy at this position. And now we're going to look at the gravitational potential energy in this position. So that's mg 2r, because the height of the loop is 2 times the radius, so 2r. And then here, the kinetic energy at the top is half mv squared. So hopefully you can see two things in this equation. We've got this v squared component, which I can now replace from up here. And there's also a mass in each of these terms, which means I can cancel out that mass. So it's irrelevant what mass the object has. This is always going to work out the same. Okay, so let's do some simplifying of this. So g delta h here equals g to r plus half. I'm going to substitute in this here, gr, in place of v squared, and we get half gr, and we can do some more cancelling. So now we've got a g in each of the terms, so we can get rid of that. And then we get delta h is equal to 2r plus 1/2 r, which is equal to 2.5 r. So that's for any height in any loop. It's always going to be the same. So for this one, the height is going to be 2.5 times a 5 meter radius, which gives us a 12.5 meter height required at the start. There's a really cool scholarship problem about this one. We haven't done anything about rotational motion yet, but if you roll a ball down the ramp, at the top there's gravitational potential energy, kinetic energy, and rotational kinetic energy, and all of this simplifying comes out the same way, and you come out with a really simple answer from what is a really complicated formula at the start. Alright, on to the next question.